In today's world, communication networks are a critical foundation of our way of life. In the 2030s, the demand on the networks and computing resources on which information services depend will be still higher than today. Collaboration among data centers, collaboration among edges, and collaboration between data centers and edges will be needed. Some estimates say that forming such links will require 50 times current levels of communication capacity. One approach to achieving this goal is high-speed distributed computing. Computing centers that are connected to each other, but geographically separated, will need distributed processing to share computing resources according to the situation. In current systems, efficiency of distributed processing remains low. With current technology, the communication capacity between computers, known as network bandwidth, is narrower than the communication capacity within computers, known as memory bandwidth. Distributed processing under these conditions degrades efficiency due to insufficient network bandwidth and communication latency. Variation in processing performance or mismatches between computing resources and communication resources cause low efficiency. To resolve these issues, technologies such as the following will be needed. 1. Data transmission technology with the bandwidth as high as 10 terabps and the energy consumption as low as 10 picojoule per bit. 2. Data synchronization middleware technology utilizing the advantage of low latency networks between data centers or data center edge. 3. Multi-degree elastic optical network technology, assigning optical network resources matching with the server processing performances. One of the major technical challenges for 10 terabps class optical transceivers is the limitation on operation speed of optical devices. If conventional optical devices are used, a large number of optical lanes are necessary to realize 10 terabps. This significantly increases both chip size and power consumption. Thus, we cannot realize 10 terabps class optical transceivers for distributed computing within 100 watts with conventional optical devices and transceiver architecture. To achieve both target transmission capacity and target power consumption, new approaches are needed. Photonic devices consisting of 3-5 semiconductors or silicon have been commonly used in conventional optical transceivers. 3-5 semiconductors are advantageous in terms of high-speed modulation and low driving voltage. On the other hand, silicon has advantages in the miniaturization and large-scale integration of photonic devices. However, no material has satisfied all requirements so far. Now Petra has developed a heterogeneous integration technology that makes these superior properties available. This heterogeneous integration technology is the best of both worlds, achieving excellent performance on all counts. On some aspects, such as low driving voltage and the integration of light sources, performance outstrips even single material devices. Thus, this technology achieves photonic devices that allow both high-speed operation and low power consumption. In addition, in terms of transceiver architecture, we need to develop an innovative transceiver architecture that can offload some functions of digital signal processing to photonic circuits. This would significantly relax power loads in digital signal processors that have large power consumption. To address these issues, we propose a high-efficiency, high-speed processing, distributed computing system using optoelectronics with heterogeneous integration. This technology consists of three main constituent technologies. 1. A photonic integrated circuit technology with direct bonding between heterogeneous materials, using the advantages of multiple semiconductor materials. 2. An architectural technology for a 10 terabps class, low power consumption optical transceiver. 3. Multi-degree elastic architecture and middleware technology for fast synchronization among multiple distributed databases. Hetra is working on proving systems for integrating these three elements, standardization of development technologies, and in partnership with universities and others, research on revolutionary devices. In the first R&D item, Hetra is building a fabrication process line focusing on the realization of photonic devices using heterogeneous integration. Using the fabrication process line built in this project, we are aiming to achieve large-scale photonic integrated circuits using heterogeneous integration. This project to develop photonic integrated circuits using heterogeneous integration is divided into 4 sub-items that we are examining. The second R&D item is research on the transceiver architecture. As a promising candidate for future optical front-end, we are developing an optical digital-analog converter transmitter technology. This solution achieves low power consumption by offering digital-to-analog signal conversion from electronics to optical domain. In the third R&D item, we are conducting research and development on a multi-degree elastic network architecture that provides optical network resources according to the status of each computing resource. This research item includes a communication resource allocation algorithm for optimal mapping between computing resources and transmission resources, a method of transmission quality control for dynamic optical path switching, and management and control mechanisms considering parameters specific to the 10 terabps transceiver. In our research and development of middleware, we integrate distributed replication technology to achieve fast and highly reliable data synchronization in distributed databases shared across multiple data centers. In R&D Item 4, we conduct a demonstration of operation that integrates the results of R&D Items 1, 2, and 3. In R&D Item 5, we are exchanging information with related standardization organizations and forums, and tabling detailed proposals on standardization to put them into practical use. Finally, in R&D Item 6, working mainly with universities, we are aiming for an optical transceiver that exceeds 10 terabps, striving for the revolutionary technologies of the future.